Hello everyone, welcoming you to Shaurav's classes. And today we are looking at the General Economics Paper 1 of the IES 2022 and question number 5 and part A first. So consider a three variable linear regression model in deviation form, which is yi equals to beta 2 x2 plus beta 3 x3 plus ui, and we have a sample of size n, where ui is the spherical disturbance term. So spherical disturbance term means that it satisfies all the standard Gauss-Markov assumptions. That's what it means. Would you estimate the parameters beta 2 and beta 1? Now, I feel that there is a slight typo in this question because if since the question is asking would you estimate the parameters beta 2 and beta 3, the answer is obviously yes, we can and we will. Now the question is how we will estimate it. So let me go take you through that process over here. So we are in part A of the question. So part A, where small yi is equals to beta 2 x2i plus beta 3 x3i plus ui. This is my model, original model, I running from 1 to n. Over here, small yi is basically in deviation form, means there has been taken a difference about the mean. Similarly, what is small x2? It is capital X2 minus x2 bar. And what is small x3? It is capital X3 minus x3 bar. These are the three things that has been done. So now obviously in order to estimate this, so what would the estimated model look like? It will be small yi hat equals to beta 2 hat x2i plus beta 3 hat x3i. Okay, and to estimate this model we will use, so by estimating the model I mean to estimate the parameters of the model, that is beta 2 hat and beta 3 hat, we use the OLS technique, ordinary least square, that we have done. We use the OLS method. Therefore, what do we do in OLS? For just recap, we have already seen it in case of the simple models. So what is the error in that we encounter by fitting this model? It's small yi minus yi hat. This is the error, right? And what does the OLS do? It tries to minimize the sum of squared error terms by choosing beta 2 hat and beta 3 hat. That means choose beta 2 hat and beta 3 hat in such a way such that the sum of squared error is minimized. Now if you look at this expression, if I denote it by S, what is this? It is, I'll just drop the subscript I for convenience. It is summation small yi minus small yi hat, right? Now you have the data on yi, x2i and x3i, so this can be easily written as yi minus beta 2 hat x2i minus beta 3 hat x3i whole square, right? So this is what you wish to minimize, and you wish to minimize this with respect to beta 2 hat and beta 3 hat. So what you will do, you will partially differentiate this s with respect to beta 2 hat first and set it equals to 0. So this gives us minus 2 out summation yi minus beta 2 hat x2i minus beta 3 hat x3i whole into your x2i, and that is equals to 0. And similarly, again taking the partial derivative of s with respect to beta 3 and setting it equals to 0. Del s del beta 3 equals to 0. So minus 2 taken out, and this will be yi minus beta 3 hat, sorry, beta 2 hat, this will be, so beta 2 hat x2i minus beta 3 hat x3i multiplied by x3i, and this whole term is equals to 0. So these are the two normal equations that we get. So from these two normal equations, so there are two equations and we have two unknowns, so we can easily get to that. Now I'll just rearrange these two normal equations so that it's easier for us to solve. So we can basically write this in this format: summation yi x2i. So this is my equation 1. It will be beta 2 hat summation x2i whole square plus beta 3 hat summation x2i x3i. This is, I've just rearranged the first normal equation in this way, and similarly doing it in exact similar fashion for the second one. So this is summation y3i equals to beta 2 hat summation x2i x3i plus beta 3 hat summation x3i whole square. So this is equation number 2. So now you can solve it in many ways. Now I'll prefer to do it using the matrix notation. So this set of equations can be easily written down in this way. So just check it out. So in matrix form, you can write this set of linear equations in this format. So first of all, I'm dropping the I subscripts so that it's not really cluttered. Multiplied by beta 2 hat, beta 3 hat, and this is equals to summation yx2 summation yx3. Okay, so now easily we can say, therefore, how will we solve for beta 2 hat and beta 3 hat? We'll just invert the coefficient matrix, that is summation x2 square summation x2 x3 summation x2 x3 summation x3 square, this matrix inverted and then multiplied by this RHS vector. So what do we get? Inverse of a matrix is adjoined by the determinant. So this will be summation x2 squared summation x3 square minus summation x2 x3 whole square in the adjoint. So for the adjoint, what we do is basically, for the 2 by 2 matrix, swap the elements of the principal diagonal. So summation x3 square summation x2 square, and then multiply the off diagonal elements with a minus sign. Okay, therefore now doing the multiplication. So what is beta 2 hat and beta 3 hat over here? It is the determinant part will remain summation x2 square summation x3 square minus summation x2 x3 whole square into, so this will become summation yx2 summation x3 square minus summation yx3 summation x2 x3, and the denominator it will be summation yx3 summation x2 square minus summation yx2 summation x2 x3. Okay, so just a normal multiplication that has been done. This is a 2 cross 1 vector in case if you are confused. Therefore, what are my final values? So what is beta 2 hat? It is summation yx2, this multiplied by summation x3 square minus summation yx3 summation x2 x3 whole thing divided by summation x2 square summation x3 square minus summation x2 x3. whole square. And similarly, beta 3 hat is therefore summation yx3 summation x2 square minus summation yx2 summation x2 x3 divided by summation x2 square summation x3 square minus summation x2 x3 whole square. And these are the parameter estimates that you get from the OLS technique by fitting the above model. Thank you. Okay, so now moving on to the part B of the question 5 that we are coming into. So let's have a look at the question first. So we consider the following data. Summation x is 20, summation y is 40, summation xi minus x bar is 40, summation yi minus y bar whole square is 124, and summation xi minus x bar into yi minus y bar is 70, and n is equals to 5. And so the first part is estimate the parameters alpha and beta of the model. And part 2 is estimate the standard errors of these estimates and how would you test for beta given a critical value. Okay, so we had already discussed the way of estimating the simple linear model in one of the earlier videos where we addressed one of the questions which has come in the IES paper. So I'm not going to ponder into the derivation of the formulas, but just going into the hint of the way we are going to do that. So the first information that is needed is that we are given that the sample size is 5, summation x is basically 20, summation y is basically 40. So this basically tells us x bar is 20 by 5, which is 4, and y bar is 40 by 5, which is equals to 8. Okay, and what was the expression for beta hat over here? Beta hat was found as summation xi minus x bar into yi minus y bar divided by summation xi minus x bar whole square. So these values are directly given to us in the question. So the numerator has been given to be 70 and the denominator has been given to be 40. So this is 7 by 4. And how do we find alpha hat? If you remember, alpha hat is basically y bar minus beta hat x bar. So y bar is 8, beta hat is 7 by 4 multiplied by x bar. So the 4 and 4 will get cancelled. So 8 minus 7, alpha hat is 1. That is what we get. Now coming to the standard errors of the estimates. So if you remember that what is the standard error of beta hat that we have obtained? It was sigma hat square divided by summation small xi whole square and taking a square root over this entire thing. Correct? And similarly, what is the standard error of alpha hat? It was a square root over sigma hat square summation capital Xi square divided by n times summation small xi square. So now note one thing, in order to get these things directly, so let's focus on the standard error of beta hat first. Summation small xi is basically summation xi minus x bar whole square. So this data is available for us. It has been given to be 40 in the question itself. So the denominator can be done. But how do we get the value of sigma hat square that is needed, right? So what was sigma hat square in this case, if you remember? It is basically defined as RSS by n minus 2. And what is RSS? Sum of squared errors. This is how we calculate sigma hat square in our case. So we first need to get hold of this thing and then we can obtain. But again, we don't have summation ei square. Then how we are going to get to this? Then only we can do this. So the once we are clear about how we are going to calculate the standard error of beta hat, and easily you can understand just by having some minor tweaks you can get to the standard error of alpha hat as well. So let us get into this part first. So the fundamental part is now in order to get to sigma hat square we need to have an estimate of RSS, that is the residual sum of squares, which is summation EI square. This is how we are going to go about this. Now look at the question. If I just scroll it up once, this information has been used, this information has been used, this has been used, this has been used, but summation yi minus y bar has not been used. So what is summation yr minus y bar, which is given? Summation yi minus y bar whole square has been given to be 124, and summation yi minus y bar is summation small yi squared, which is given to be 124. Now we know one more thing, that from our ANOVA analysis, that this is essentially the total sum of squares, and this can be split up into two parts, which is the explained sum of squares plus the residual sum of squares. That means the explained sum of squares is something that is the proportion of the variance in y that can be explained by x, and the residual sum of squares is something which cannot be explained by x. So you can understand that if we can now obtain the value of ESS from the data that we have, then we can directly compute the RSS as TSS minus ESS, right? This is what it is. And if you remember, what is the explained sum of squares? It is basically computing this expression, summation yi hat minus y hat bar whole square. This is what was the explained sum of squares. Now naturally we don't have values for any of them over here. That's pretty convincing. So how do we get about this? So this is basically often denoted as summation small yi hat whole square. Now let's get into the model so that we have a better idea of how we can calculate this thing. So now what was my original model? It was small I capital yi equals to alpha plus beta xi plus ui, right? And I was basically running from 1 to 5. 5 observations were there. And what is the estimated model looking like? Small capital yi hat equals to alpha hat plus beta hat xi. And how do you estimate this model? Using the OLS method, right? Now observe one thing, that if you take the mean of this, so you have y hat bar is equals to alpha hat plus beta hat x bar, right? And if you take the difference, what essentially do you get? yi hat minus y hat bar is equals to beta hat times xi minus x bar, correct? That means this is basically small yi hat, which is beta hat times small xi, correct? Now if you take the square on both sides and take the sum, observe that the expression on the left side is nothing but the ESS, and this can be now written as the beta hat is a observed value, so estimated value. So this is beta hat square summation small xi square. So we can directly obtain that. So now we can obtain the ESS as beta hat square summation small xi square, which is just for notational convenience. I am just rewriting it as capital Xi minus x bar whole square. So what is beta hat? It has been obtained to be 7 by 4. So this is 7 by 4 whole square, and this multiplied by 40. So that is 49 by 16 multiplied by 40. So this will go 5, sorry, 4, 4, 10, 5, 2. So 49 into 5 divided by 2. So that is 245 divided by 2, which is 122.5. So this is my ESS. Therefore, what is my RSS? It is TSS minus ESS. So TSS has been given to be 124 and DSS is 122.5, which is 1.5 straight away over here. Therefore, what is sigma hat square? It is RSS by n minus 2. So RSS is 1.5, n minus 2 is 5 minus 2. So 1.5 is 3 by 2 by 3, which is basically turning out to be half, 0.5. So now we can understand how this is obtained. So now having obtained sigma hat square, now standard error of beta hat can be easily obtainable. Um, so that is sigma hat square divided by summation small xi square. So that will be half divided by 40. So that is square root over 1 upon 80. So we can just split it up. 80 will be 16 times 5. So this will be 1 by 4 root 5. That is the standard error of beta hat. Okay. And similarly, if you look at the standard error of alpha hat, so what was the expression that I had written? It was sigma hat squared summation capital Xi square divided by n times summation small xi square. Now note that sigma hat square has been obtained and both the terms in the denominator are known. But we are not given the data on what is summation capital Xi square. So what we can do, a simple tweak in the expression will work. So sigma hat square remains summation capital Xi square from the properties can be written in this format. Summation xi minus x bar whole square minus nx bar square divided by n times summation small xi square. Because note this thing, in the properties of variance and other things you might have learned, that 1 by, if you have a data something like 1 by n summation capital Xi minus x bar whole square, you can write it as 1 by n summation capital Xi square minus x bar whole square, and just taking the n out, so that will be summation capital Xi square minus n x bar whole square. So summation capital Xi minus x bar whole square plus n x bar whole square will be summation capital Xi square. So sorry, it will be plus over here. Okay, this makes sense. So now you can easily just substitute the values. Sigma hat square is basically coming to be 0.5. Summation capital Xi minus x bar is 40 plus n is basically 5 and x bar is basically 4. So 4 square divided by n is 5 and summation small xi is again 40. So you basically have this as square root of 0.5 times 40 plus this is 16. 16 into 5 will be your 80. So 80 plus 40 will be 120. So okay. So half of 120 divided by 5 into 40. So that will be square root over 60 by 5 into 40. So this and this will cancel out. So that will be 3 2s are. So root over 3 upon 10. That's your answer for standard error of alpha hat. Okay. So now the next part of the question was How would you test for beta hat and given this critical value? T of 0.025 comma 3 is basically 3.182. So to test for beta hat, sorry, to test for beta. So test for beta. What is my hypothesis that we want to test? H naught beta equals to 0 versus alternative hypothesis H1 beta not equals to 0. So what is my test statistic in this case? Beta hat minus beta, the expected value, divided by standard error of beta hat under H naught will follow a t distribution which n minus 2 degrees of freedom. So in this case, under the null hypothesis, beta equals to 0. So we basically boil down to this. Beta hat by standard of beta hat will follow a t distribution with n minus 2 degrees of freedom. And here it is basically, if I can just write it directly, n minus 2 is basically 5 minus 2, which comes down to 3. Follows the t distribution with this 3 degrees of freedom. And what is the testing rule? We will reject the null hypothesis if the absolute value of the test statistic is greater than the critical value. So in this case, t of 0.025 comma 3, and it has been given to be 3.182. So we basically need to check this. Simple. 3.182. So let us compute this first. So beta hat by standard error of beta hat is basically, beta hat is 7 by 4 and standard error of beta hat is 1 by 4 root 5. So that is 7 into 4 root 5 divided by 4. So the 4 and 4 will get cancelled, and this is 7 root 5. Right? Sure. So 7 root 5 is the answer, and we need to compare. Now, without actually going into the entire calculation of the square root and all, if you don't remember, one thing you can understand, right? That square root of 4 is 2, right? So square root of 5 is something greater than 2, right? So 7 times square root of 5 is definitely something greater than 14, for sure, whatever the value is. So whatever will be the value, that is great, definitely greater than the critical value. So hence, we will reject H naught at 5% level of significance. So that's the answer to the final part of question 5. Thank you.